Yes, I am going to go through some of the commonly missed problems from the Kahoot, different types of problems here. We're going to start with a common external tangent problem. They told me that the big radius was 8, that the small radius was 2, and that's all that they gave me. They inadvertently gave me the distance between the two centers. Notice that that is the sum of those two radii. So that should be 10. Sometimes they tell you what the distance is between the two centers, but if they are externally tangent, if they meet at a point, then they really don't need to. Right now, I have myself a right trapezoid, despite what it looks like, because where a tangent meets a radius, they form right angles. And I'm going to trade in my right trapezoid for a right tangle, which is a funny way to say rectangle, but I'm emphasizing the rightness of it. So that is a right angle. And again, this is a right angle supplementary to it. If this side of the rectangle is 2, then the opposite side of that rectangle is also 2. And notice that this whole thing has to add up to 8. So this side of the triangle must be 6. Now I know 2 out of the 3 sides of the right triangle, but there's no need to bother Pythagoras because it is a 6 blank 10. That, of course, is a 3, 4, 5 triangle, slightly larger. It is a 6, 8, 10 triangle. And again, if we know one side of a rectangle, the opposite side must be 8 as well. So that is that process. We'll get another opportunity to look at that below. Here is a walk-around problem, and walk-around problems work a little bit differently if I have an even number of sides versus if I have an odd number of sides. Got cut off a little bit. A is up there at the top. They tell me that AC is 4. They tell me that AB is 7. And they tell me that BC is 5. If it's an odd number of sides, they usually give you all the sides and have you find one of these tangent segments, BX. This must be an X over here. So I'm going to label this with a D if 2 tangents come from the same point. So like BX and BZ, 2 tangent segments really, then they are congruent. So that must be a D as well. This must be a 7, the length of the whole side, minus D. Switch to a lowercase for no apparent reason. And if 2 tangents come from the same point, then they are congruent. That must be a 7 minus D as well. This segment YC must be the length of the whole side minus the length of AY. So I get a positive D because a negative, a positive D and a negative 3. I get a positive D minus 3 over there. Well, I've got a D and a minus 3 equals 5. I've got 2D minus 3 equals 5. I've got that 2D equals 8. And I've got that D equals 4. Okay. So I found this length to be 4. I can figure out the other lengths if I want. If that's 4 and the whole thing's 5, then this one has to be 1. There's a 1, a 4. This one would have to be a 4 as well. That one would have to be a 3 as well. This one would have to be a 3 as well. And a 3 up. And here, with a 4 as the whole side, well, this side would have to be 1, but I knew that anyway. All seems to work. Let's revisit one of our common external tangent problems. I will draw in these radii, which must be perpendicular to the tangent that they intersect. And I will also draw in the distance between the 2 centers. The radius of the 2 circles below are 3 and 8 this time. So this guy is a 3, that guy is an 8. And the distance between their centers is 13. When I draw in the segment to form my rectangle, remembering that there is my right angle, there is another right angle. Don't put the right angle in the wrong place, well, then this has to be 3, this has to be 5, and now I'm faced with a 5 blank 13 triangle. That would be 12. The opposite side of the rectangle is also 12, and that one is solved. Let's move down to the other walk around problem. They told me in this case that AB is 10, that BC, which is down here, is 15, that AD is 12, and my job was to find the other side. Literally, I will walk around this problem. I'll start by calling this segment X. Again, it's not what I am looking for, and in a quadrilateral or any even number of sided polygon, I'm not going to be able to figure out what it is, but I can use it. That would be X. If two tangents come from the same point, then they are congruent. This would be 12 minus whatever is over here. So 12 minus X. And this is congruent. It must be 12 minus X. The whole side is 10. So this is 10 minus whatever's over here. It's a little bit more complicated because it is 12 minus X. And before I go on, I'm going to simplify. 10 minus 12 is a negative 2. And minus a negative X is a positive X. I'm going to write it as X minus 2. And R to the dot should also be an X minus 2. If two tangent segments come from the same point, then they are congruent. Likewise over here, this should be the whole thing, the whole side, 15 minus whatever's over there, X minus 2, 15 minus X, and then minus a negative 2 would be adding that to, I really end up with 17 minus X, 17 minus X, and when I add these two sides together, the X's go away. X plus 17 minus X plus 17 minus X. Goodbye X's, I'm left with 17. Okay, the final type of problem that I want to try here is a common internal tangent problem. And I've got two different ways of doing these. The book way is a little bit easier, perhaps, but my way involves similar triangles. So I kind of like them both. Okay, so in the book way, what you do is you take the radius here, which they are telling me, I believe they told me was 6, and extend it by this radius, which they told me was 3. Okay. I'm going to draw in the distance between these two centers, which they told me was 18. And I am going to draw this segment, which comes back over here. From the end of this extended side, which is now a 6 plus 3, and it should be parallel to this. Well, that formed a right angle. It was a radius intersecting a tangent. So this is a right angle here. And now I have two sides of my right triangle. Once I find this length is the same as that length, it is, after all, a rectangle, despite what it looks like. And hopefully, again, we don't have to bug Pythagoras here, because if one of the legs is 9 and the hypotenuse is 2, there's only one triangle where the legs, or one of the legs, is half of the hypotenuse. And that, of course, is a 30, 60, 90 triangle. So if opposite the 30 is x, opposite the 60 should be x root 3. So this should be 9 square root 3. And let me do that exact same problem one more time my way. So exact same problem, exact same stuff going on here. This guy had a radius of 3. This guy had a radius of 6. And the distance between their two centers was 18. I'm not going to write 18 for the time being. Instead, I'm going to remind us that that must be a right angle and this must be a right angle. Where a radius intersects a tangent, they form a right angle. And these two angles are congruent. I have some similar triangles through AA. So regardless of what this length is and what that length is, they must be proportional to 6 and 3, which I'm going to use. Of course, I could reduce it to 2 and 1. So this length I'm going to call 6x. And this length I'm going to call 3x. Together, they are 9x. And I didn't want to put in what that length was beforehand because it wouldn't have fit real nicely into my diagram. But there it is. Together, they're 18. Well, I guess x equals 2, and 6x must be 12, and 3x must be 6. Got myself a right triangle with a 6 and a 12. Again, it's got to be one of those 30, 60, 90 triangles, only right triangle where one of the legs is half of the hypotenuse. So this must be 6 square root 3. This must be 3 square root 3. After all, they are proportional. And together, they are 9 square root 3, the length of that common internal tangent. Let's scoot back over to this one. I'll do it in reverse order this time, where I will do my method first and the book method second. You don't have to know both. You don't have to be proficient in both, but they both do work. There's a right angle. Here is a right angle where a radius intersects a tangent. They are right angles. This time, again, this was 3, and this was 6. And this time, the distance between the two centers is 9 square root 2. So when I call this 3x and I call this 6x, this time 9x equals 9 square root 2, and cross out those 9s, x equals square root 2. So 3x is really 3 square root 2. 6x is really 6 square root 2. I realize it's getting a little squishy in there. Let me zoom in a little bit there for you. And now I've got a right triangle where one of the legs is 3 and the hypotenuse is 3 root 2. Oh, it's another famous triangle. It's a x root 2. So if x is 3, then that's a 3. In this case, if x is 6, then that's a 6. And 3 plus 6 is equal to 9. That's my length of the common internal tangent. Let me flip it over, do that exact same problem, which had a smaller triangle and a bigger triangle. We had a common internal tangent. My larger radius was 6, and I am going to extend that by the length of the smaller radius of 3. That is a right angle. This is a right angle and a right angle. And that is a rectangle. So if it is a rectangle, then that is a right angle. And this is a given length. This again was 9 root 2, 9 root 2. So let's kind of ignore this line in here for the time being. I'm going to kind of cross it out a little bit. And I've got this triangle, which is 9 root 2 and 9. Oh, It's a 9, 9, 9 root true triangle. If that is a 9, then this is a 9. And again, we have found that that common internal tangent has a length of 9. There's one other problem which I want to do, so forgive me while I pause for just a moment and bring it up. Okay, this was a problem posed to me by one of my students. The name of the game is Finding Angle W, and despite my my inability to draw it, this line here is supposed to be tangent, so I just made it kind of a big dot there. Well, if this is 150 degrees, it must be supplementary to this angle, which is 30 degrees. And that's all I need. This is technically a tangent chord angle. I will refer to it as inscribed because its vertex is on the circle. Here is a really inscribed angle. Its vertex is on the circle. And it is eating a congruent arc. I know the arcs are congruent because the chords are congruent. And if two inscribed angles intersect congruent arcs, then they are congruent. And that guy must be 30. If we don't believe it, we can use some of our rules and say, hey, the inscribed or the tangent chord angle always tries to eat a arc which is twice its size. So this guy must be 60. Again, if chords are congruent, then arcs are congruent, and this guy would be 60 as well. And again, an inscribed angle is trying to eat something twice its size. So if that's 60, it must be 30. And we are all good. All right, thanks for watching. Bye.